It's kind of an interesting exercise. The losing candidate in the election is asking all the voters for a urine sample. So we can learn more about them. But I want to explain it to you because some of you may want to participate. I think some of you may already be participating. And I'll explain. While he's waiting, I'll show a brief calculation. I made an argument by assertion a little while ago when he was speaking about nuclear power. Palo Verde produces its power at 2 cents a kilowatt hour. If it sells it to Los Angeles, which is where its power is sold, it sells for about 12 cents a kilowatt hour, so it can make 10 cents on each kilowatt hour. If you work that out, that's $900 million a year, or 3 years to generate the capital to build Palo Verde. That's what it costs in real cost to build Palo Verde, not what it costs today when the government adds 3 or 4-fold more to it. So that plant, if built under realistic conditions, could pay for itself in 4 years and then give us a river of 2 cent kilowatt hour power for another 30. I'll put those numbers in access to energy. This is sort of this is a mass spectrum of urine. And I got into this problem because of thinking too much when I was a young man. I've been dreaming about this for 40 years. When I was a student, I had many opportunities and I could spend my life in basic research. When I got out of graduate school, I said to myself, hey, this is fantastic. I'm going to get to play all my life and people are going to pay me for it. And then I got the idea that I should do something in return, and so I decided I'd do some medical research to make up for that. And the problem, Pauline and I started working together. We were working on nutrition and preventive medicine, on mental illness, and all kinds of things regarding human health. But the problem, the central problem, was the quantitative measurement of health. And today, you still have this lack. There's no quantitative measurement of health. So for example, we wanted to make a graph of the amount of vitamin C you eat as a function of your health. If you don't eat any, you have no health, and as you eat some, it rises, and as you get to an optimum, it's a maximum, and if you eat too much, your health falls. You can't make that graph, because there's no way to measure the health that goes on the left-hand axis. And this is true of, in general, there's no quantitative way to measure aging. There's no quantitative measure to follow disease, to see it early, to see the probability of disease, or if you already have a disease, a quantitative measure to watch its progress, so that you can evaluate the therapy that you're trying and see if it's good and what the rate of progress of the disease is. So we searched for 10 years with about 20 scientists working hard to figure out on the basis of an idea. And the idea was that if we measured enough of the metabolites in a urine sample or a breath sample and then did computerized pattern recognition on them, we would be able to find we'd be able to take those patterns that we found that were characteristic of different aspects of human health and condense them onto linear decision axes, as is shown on the 4th page of this flyer I gave you. And if we could do that, we'd have a quantitative measurement of health. In those days, it was very difficult to do. After 10 years, we built what was then the finest analytical lab in the world for urine and breath, and we had about 200 substances. This is pretty good. At the doctor's office, if you give them a urine, or you don't give breath samples, but you could, urine or blood sample, they measure about 20 things, about the same 20 they've been measuring for 75 years. And they're looked at one at a time by the doctor, rather than as a whole, because he can't compute patterns in his head. So we got to 200, and I give an example of an analysis in here that we did. We measured about 15,000 urine samples, and we found patterns for multiple sclerosis, muscular dystrophy, breast cancer, aging, and then a lot of simpler things in these samples. It was a very powerful technique, and it was the beginning of something that's now called metabolic profiling. The problem was that the analyses took a long time. They were fairly expensive to do. So we published all this, we originated the field, but we didn't do anything for people's health. Well, over the last 30 years, this work started in the late 1960s. Over the last 30 years, the technology has marched ahead, both the analytical technology and the computer technology. And so this is where we are today, and this is not in your brochure. This is a mass spectrum of a man's urine. If you're already in our project, and some of you are, it might be your urine. It took 10 microliters, which is about 1/3000th of an ounce of urine, and you see from 200 to 700 mass units. So each of the bars, the height of the bar, is the amount of substance at that mass. So you would have 200 to 700, but there's a problem because they overlap. You see, you can have several different chemical compounds, and these are all substances which are either metabolites, either produced for positive reasons or negative reasons while you live, and then cast off in your urine. You can do the same thing with breath. Each of those represents more than one compound. They're on top of each other. And because you could have the mass, you can get the same mass by adding up different numbers of carbon, nitrogen, and oxygen atoms in the organic compounds. But because of the nuclear binding energies being different in nitrogen, oxygen, in the different atomic nuclei, the masses aren't quite integral. You know, carbon is defined as 12, nitrogen is 14, but nitrogen not quite 14, and oxygen is not quite 16, and hydrogen is not quite 1, and then the isotopes. And none of these are integral because the nuclear binding energies are a little different in every atom and isotope. The consequence is if you have a high enough resolution mass spectrometer, you can separate these bars. And you can see there separations of several of them, then there's a separation of one. The bottom line is that you can see, well, you can really see almost 10,000 compounds in there. You can easily measure quantitatively 2,000 of them. And this is from an experiment we did on men. And it isn't published yet, but it will be soon. And some of you, I think, were men in that experiment. We did an experiment long ago with these primitive techniques, and we showed we could determine what age an individual was chronologically within a certain range of accuracy. It wasn't too accurate, but it was pretty good. This, with 2,000 compounds, you can get a very, very fine answer. Now, you already know what age you are, but the question is, what is your physiological age? How fast are you aging? If you, for example, were to read an article in a magazine and it said, boy, if you exercise, you'll live longer. You'll physiologically age more slowly. Or take vitamin E or some other thing that you might do. You have no way to know whether that's true. You can take it as long as you can stand it, and then you read another article, do something else. Martin Kamen, my thesis advisor, used to say that he noticed that people who exercised lived longer by about the length of time they were exercising, so he didn't think it was worth doing. But that's the point being that you can't measure it. However, if you had something that was sampling your breath or your urine routinely, and pattern recognition was done in your computer, you might have a line you could call up on your computer which showed you the rate at which you're physiologically aging. Then you could make some change in your life and see if the rate changed. Now, that is the aging being a sort of a compilation of all the things that might kill you. You might be more interested in what the probability is that you'll get cancer, or what's the probability you'll have a heart attack. Or if you already have a disease, you might be interested in the rate of progress of the disease. When you have 2,000 organic compounds produced by a person in his body fluids, you have definitive information about these things. You can do these things quantitatively. This field has advanced tremendously. A lot of work has been done. And this machine, this is sort of a miracle in a box. This mass spectrometer has a resolution of 1 in 10 million. You can actually, you don't have to calibrate where the masses are because you can resolve something at every mass. It's an unbelievable thing. It's very sensitive. You can only give it 500,000 molecules at a time. And we used to work in a chemistry laboratory we built. If you look in our old laboratory, you'll see flasks and vials and all the wet chemistry things that a biochemist uses. If you go into our laboratory today, you see nothing but a mass spectrometer, because by being able to see every molecule quantitatively and trivially at extraordinary sensitivity, everything an analytical chemist wants to see, it can be seen by the single device. And it's very fast. You can do this in a very short time. There's one deficiency that has always been present in this research field, and that is a set of calibration samples to calibrate it. Let's say, for example, I have a machine sitting in the corner, and I tell you that that machine is a fabulous analytical machine, a fabulous computer. You breathe into that machine, and I can tell you the probability you'll have breast cancer before you know. Well, it's probably true. The power of the techniques are incredible, but I can't prove that because I have no samples from women who before they got breast cancer. You would need to have samples from people before they got a disease to see if the machine could see the disease before they knew they had it. And of course, if you can find a disease before you know you have it, you can fight the probability of disease rather than disease itself. It's useful for measuring things which, like I mentioned with aging, for measuring things that relate to your overall health. It's useful for seeing diseases before they occur, for diagnosing them, and when you're sick, it's very important. You know, you're sick, you get some dread disease. You go to the doctor, he says, well, you're going to do this. Come back and see me in 3 months if you're still alive. You're not measured every day to see how you're doing. And there's one graph in there that is indicative of what this means. If you look at the death curve of human beings, it's there. That's for men quite a few years ago. You start out at 100% alive at 0 time, and then as time passes, the curve diminishes and goes down. More and more people die, and then there's kind of a tail on it going out to about 100 years. It's there in the second page of this flyer that was in your handout. Well, this isn't right. If you do the experiment on fruit flies in the laboratory and take care of them, the curve is square. You don't have the early deaths. They come out like this, and then most of them die at their intrinsic lifespan. If you take care of mice, most of them die at their intrinsic lifespan. You don't have these early deaths. We don't have to experience those early deaths either, but one tool that our medicine is missing is the ability to measure our health and our probability of illness and the degree of illnesses we have quantitatively so that we can objectively change our lives in such a way to avoid those early deaths. Anyway, the only way to do this is to build a bank of samples of human beings who are well. Or if they're sick, we know what's wrong with them. So, and once we have that set, not only this mass spectrometer, but this kind of analytical devices that are in the hands of people in this research field all over the world will have sample sets they can use to calibrate their devices. So if you are interested in how soon you can see lung cancer and how it progresses once you know it and so forth, instead of waiting until you're almost dead and then having some heroic procedure performed, perhaps you can see the probability before you know you have the disease, fighting it more effectively. And even after you have the overt symptoms of the disease, you have a quantitative measure of how fast the disease is progressing so that you can adjust therapy and change therapies if it's not working. I think you understand. In any case, we started a project, and we have the analytical capability, but we also have the cryogenic capability, and our goal is to store urine samples every 6 months for 15,000 people over a period of 5 years. And the disease incidences are such that after that time, we will have a set of samples from people who contracted most of the diseases that affect people's health during that time. So we'll have samples, and we'll have enough of them so that we can do a statistically significant experiment. You have to have perhaps about 20 samples from people who are in one group and people in another group before you can make these distinctions. Today, you go to the doctor, if he takes a urine sample, usually use a dipstick, but at best he measures 20 things. But the chemicals in that urine are a total fingerprint of who you are. One of the things we did in the old days, with only 200 compounds, it's just like a fingerprint. I can tell whose urine it is. Once I've seen one, I'll know it came from the same individual. Your urine is a total fingerprint of you, a total fingerprint of your genetic character, but it's also a fingerprint of your health. And with 2,000 compounds measured quantitatively, there's probably no aspect of a human's health that can't be measured quantitatively by these devices. So our goal is to build this bank. There are a lot of ways to build the bank. When we started on this work, all of us were living on synthetic diets. We decided, oh, no, don't any dietary variation in this stuff, so we'd all live on chemically synthetic diets. And when I first took my wife, Laura Lee, out to dinner on our first date, she ate a dinner and I was drinking a purple liquid because I was on the experiment. Well, diet control, it makes, of course, takes away some of the experimental variation, but it's completely impractical. You can't expect people to go on a synthetic diet for a week to see what their health is like. There are other things. You can go, it'd be nice to have the sample immediately, so you could immediately freeze it at minus 80 degrees, so there'd be no changes. But that also is a little impractical. It's more likely, since if this sort of technology is used by people, it's more likely they'll send you a urine sample in the mail, pay $5 for the analysis and get the information back. And if you send the sample in the mail, of course, there's a day or two when there can be some chemical changes, so the substances that change will not be necessarily the ones that you use for the analysis. In any case, this is being sent, this is a flyer, it's a draft. After I get home, we're going to send it to the 40,000 people in Josephine County, Oregon. They gave us, about 2/3 of them voted for us, so it won't be too bad. I think they probably won't dislike us too much, but in that county, not in some of the other counties. But the idea will be if they want to participate, they cut out this thing, send it to Matthew. Matthew will send them the vials they need, and every 6 months we'll send them another set of vials. They send the urine back in the mail, and we put it in cryogenic storage and characterize the situation and wait. And after a period of 5 years, we won't have to wait so long for the more common diseases, but for the less common diseases, we have to wait 5 years. We will, for the first time in medical science, we'll have a sample bank for urine, the samples of which can be put in the hands of scientists that can get true quantitative information. It's a way of really a revolutionary thing in medicine. It is not something that has been pushed. This research, this could have been done earlier, but it's hard to make changes, especially as medicine becomes more and more socialized, more and more government control, and there are other factors. When we were working on this, I had lunch with a guy that was the vice president of 3M Corporation one day. 3M was at that time running some big clinical laboratories. And this is a $100 billion business. Measuring blood and urine samples when you give them to the doctor is a $100 billion business. And I said, you know, we're measuring 200 things, but you're measuring 20. Why don't you get a couple of good statisticians and some computers and do pattern recognition on those 20 and get more information than the doctor is able to do by just looking at them. He said, why should we do that? We're making good money doing what we're doing. And he's sort of locked in place too, because to get government permission to do that would probably cost his company $1 billion or $2 billion. So there are a lot of impediments that have stood in the way of this sorts of science being adopted immediately. Another thing about, and I left one thing out, I won't take much more of your time, we want samples every 6 months. When you give a sample to a doctor, he gets back the amounts of these 10 or 20 things that are measured. He also gets back a little range, 1 and 2 standard deviations for the human population. Then if one of your values lies outside of the standard range, he says, oh, and that means something to him from his medical textbooks. But he's comparing you to the entire population. You should really be compared to yourself. If you're compared to yourself, then you'll see changes. The techniques are far more powerful if your pattern is compared to the pattern you had in the years preceding that. I'll close by mentioning one thing. When we had our meeting once down at Palo Verde, and Ed York, who was an extraordinary man, many of you know him, he spoke here, was standing beside me. We were looking at this turbine generator of Palo Verde. And it's incredible, you know, this gigantic room, and the shaft is huge. It's a beautiful piece of machinery. that thing is sitting there generating, 1,000 megawatts of electric power. And Ed stood there, he says, you know how they keep track of the bearings in that thing? They don't wait till they squeak, and then decide to go in and fix it. They bury a little vibration sensor in a hole near the bearing, and a computer watches the vibration, and they get a kind of a fingerprint of the vibration. They get used to what that bearing looks like when it vibrates, and then when it does something a little different, they become alarmed and look at it. That's what we're talking about here, except we're talking about 2,000 vibration sensors measuring different things, and then the very powerful things that computers can do in analyzing that information. So the reason I talked about it is not necessarily tell you what we're doing. If you read Access to Energy, you'll know, but I'm now in the business of asking people for urine samples. And interestingly, I'm finding there's an interesting difficulty in this. Having worked on breath and urine and these things all my life, to me that's another reagent, and a reagent with huge amounts of information that I want. But I've asked a few of my friends around Grants Pass, Oregon, if their businesses, they mind being drop stations for the urine samples, because it's easier than mailing them, and they go right in the freezers and get cold sooner. And I'm finding out that people don't have a very high opinion of urine. And one of them, a very close friend, the guy likes us very much, and he has a little business there. And I said, could we just drop the samples in a freezer at your business? He said, well, I don't think it might detract from the public's opinion of my business because there are urine samples here. And so it is funny. People think of this in a different way. Probably to close, I'll tell you what the world is going to look like this way for 50 years from now. In fact, if fields advance fast enough, it could be 15 years. You can do the same thing with human breath and get the same information from human breath. Now imagine that your computer, besides that little camera it's got on you so the government can watch what you're doing, has a little breath sensor in it. It's just going to sample the air in your room and do the same sorts of things I've been talking about. And that is chemically possible and analytically possible, and probably will become a computer peripheral, hopefully within the lifetime of many of the people in this room. Today, urine is easier, and it's easier for us to work with, so we're doing that. If anyone has any special questions, what I hope you'll do is clip that out and send it, and ask Matthew for some vials. Yeah.
Would blood provide even more data versus urine and breath?
No, actually, I don't think so. One is more difficult. What we want is something that costs a couple dollars, like buying a soda pop. So we want it to be cheap, and for blood, you have to have the blood drawn. But there are ways of getting around that. The substances are more concentrated in the urine and more easily analyzed there.
Okay.
I don't know. We concentrate on urine breath because we thought they had more information than blood. But I'm not telling you the answer because no one's done this with blood.
Yeah. Okay.
I've been giving samples for many years. Generally, they want you to fast 24 hours or 8 hours or whatever.
Yeah, it's totally irrelevant.
And then doesn't depend on what you eat or what you drink or.
Yeah, well, that's first. You can take a 24-hour urine. You can also just divide by all the compounds you see and normalize away the water variation. You see.
But would it depend upon your diet, what you ate the day before?
Yeah, that's right. It does. Yeah, when we started doing this work, we had all strict diet control. But if you want to help people, you're not going to have strict diet control. That's impractical.
Yeah.
And it doesn't really matter. The thing's measuring so many compounds, the diet compound, if you have a peak, suppose you have a metabolite, and that metabolite's also present in your food. So it's going up and down because of you and your food. Well, then that one won't be useful in the analysis. It doesn't matter. We have thousands more. So the resolution and the number of compounds measurable, and I should say those experiments we did in the past with only 200 compounds, the primitive devices in the 70s, we were diagnosing MS, muscular dystrophy, cancer, telling people's ages and so forth. There was no diet control at all.
And then there's
you could do it with the diet control. It'd be nicer. And it would be impractical. I could publish lots of papers, but you would never receive the benefit.
And the other complication is people are taking medications.
Sure.
Some are taking Lipitor, vitamin D,
right?
et cetera, et cetera.
These are all complications. but people are complicated. They are the worst experimental animal you could choose.
Right. Okay.
If you're a biochemist and you're doing biochemistry, you don't work on people. You work on
that's what I
people
thought.
only for a moral reason. You have to take them and you get them. And the mindset, the thing you're suggesting is where people's minds always go, especially scientific minds. I'm going to get the diet control, I'm going to get this and that, I want to get this normalized. Then I don't like it because they're all different strain, right? Because you're not the same as the guy next to you. But what we showed in the 70s, it was with only 200 compounds, we could still do a lot with all those variables uncontrolled. And now, you wouldn't believe this. In this experiment, NOAA's been calculating it. It hasn't been published yet. We've done what this experiment, I just did an experiment over we did in the 70s to see how much better this was. It's a miracle in a box. I mean, it is unbelievable in calculating what you want. Something that was maybe plus or minus 5 years before, there's almost no plus or minus in it because there's so many compounds. You just throw out the ones that get complicated by something that would worry you.
Okay. Is there big differences in people that you can see if they start or stop exercising?
I'm sorry, say that again?
Is there a big difference in what you can see in people if they start or stop exercising?
We never did that experiment. We did a lot of experiments and we only failed once. We were not able to tell which undergraduates had the highest GPAs at Stanford. We couldn't tell their GPA by the urine, but we could tell almost everything else. We could tell their sex. We could tell if the girls were taking birth control pills and not looking at any substances. You can take, for example, those of you, I don't want to use a lot of jargon, but your proteins are made of 20 amino acids. Those are the building blocks of the macromolecules that keep you alive. They're amino acids. They're not known to be related to sex or sex, you go look at some hormones and so forth. But with the 20 amino acids, you can see how old a person is and what sex they are. And those are just amino acids. And there's no biochemistry book you can read would suggest that those would be related to those conditions. But the information content is just enormous. Yes, sir.
How long does it take to fill out the questionnaires each time you give a sample?
Well, what you get a little cup to make it easy and a vial and a bigger vial to put that in because the post office wants 3 containers. And you put a few drops of urine in it and drop it in the mail, and that's it.
So
we're not doing something that will benefit you. You may never get any benefit from it. You're helping our research by being a guinea pig.
But do we get any feedback?
You probably, well, the feedback you would get would be if we publish a paper or someone published a paper using this, you'd be informed about that research. You won't probably never get anything personally from this.
So we don't see our data.
A medical procedure which your doctor gives you. We don't practice medicine. We couldn't even tell you if we found out something interesting about you. It'd be against the law for us to tell you. And we're not doing anything like that. We're doing research on the samples. We're asking you to be guinea pigs. You don't benefit at all. You get nothing for it.
Now,
I don't get anything either for it, but it's worth it.
Could you think about collaborating with NASA? They do longitudinal studies with astronauts and things that might really fit into this.
There are all kinds of things one can do. We're doing what we think is the most important thing for us to do, which is to build a sample bank so that ordinary people can be helped by the medical industry using this technique. Sure, you can think of 1,000 other things, but we don't have the resources for that. We got the resources together for the cryogenic bank. We now can store the 200,000 samples at minus 80 degrees C. We have the analytical machinery to make sure everything's being done well, and that's all our little institute's capable of at present.
Thank you.
What about the quality of the sample? If it's going through the mail for several days,
it's a
bacterial
disadvantage.
growth, that kind of thing, that's not
Exactly.
not good.
And when we started out on this project, we got a lot of little minus 80 freezers. And they're great. They're little things. In fact, you can plug them into your car lighter. They're very reliable. They have about a cubic foot of storage, minus 80 freezers. And I was going to put them in doctors' offices and drop points and so forth. And we still have that objective. If a doctor is willing to do all of the people that pass through his waiting room, we'll give him a minus 80 freezer he can sit on the table, and we don't have that disadvantage. But we want to do this project, we have to get this done. So we're going to the general public. We'll get the samples back from the general public. Doctors or institutions who are willing to take freezers from us and not have that 2-day period of ordinary temperatures, those samples will be more valuable. But if I can't get them, I'll do it with the others. And I'm certain that, and there are other things. For example, how would this be used? You're going to go to the doctor's office and pay them $100 for a visit to do this you want something people can do every week if they want, or every day, or whatever. It's like buying a Coke. And that means they're probably going to send their samples through the mail. And they probably are going to be at room temperature. Now, ultimately, what I used to think of is you'd have a little piece of absorbent paper, put a drop on there, and it would dry. If it dries, then it'll be safer than it is in the liquid form. But to know ahead of time while you're building this bank that the paper wouldn't screw you up is a big project which we can't do. I know about how fast these compounds of various kinds deteriorate, so I'm sure that 90% of the information will get to us even if it comes through the mail at room temperature. And of course, it'll be stored forever at minus 80 degrees C, so once we get it, it stops changing.
No worry there. Yeah.
And remember, it's been in you for several hours before you give it to us at a higher temperature.
That's true.
So it's clear, as soon as you give that sample, it will start to deteriorate. And some of the chemical compounds in it will lose the information that we're after.
Yeah.
But if we have thousands, perhaps we can do it in a way that is practical immediately. You see? Because there's a big difference. Do you know how huge the medical research literature is and how huge the biochemical research literature is? But very little of it reaches people and improves their lives. The thought that screwed me up in the 20s and got me measuring urine for a lot of my life was Dr. Zubrin illustrated. I thought that the highest thing you could do would be to improve the quality, quantity, and length of human life. I didn't know there was another world out there that thought the opposite. But when you do this kind of work, you're not doing this. We do basic biochemistry. We love to do it. We have a very special field we're expert in. We love to do our biochemistry, our deamidation research. But this is done for only one reason, to improve human life. So if we don't do something practical, we won't help anybody.
Sounds
we'll
good.
We'll publish papers, and somebody will say, gee, yeah, maybe if that were done in a practical way, it would help people. And we could show all our publications and go to meetings and strut around. And, but you never... All this work we did in the 70s, it founded a research field. The things we did, people didn't think could ever be done before. And we built the finest lab in the world for a purpose. And not one human being has ever been benefited from that work. We want this bank under practical conditions so that it could be immediately used for people if we demonstrate its capabilities.
Well, how many do you want from southern Arizona?
What?
How many samples do you want from my town?
I want, well, we need 15,000. How big's your town?
All right, we'll see what we can do.
Huh? We're
not that many people there.
If you're if you get very interested in this, we'll send you a minus 80 freezer or 2 or as many as you want. We'll take 1,000 samples from your town if you want.
We're very small, but
we built this for 15,000 samples. Wow. And we'd love to have people, some people actually are showing an interest in doing their whole church and things like that. And anything like that would be valuable.
As soon as you get the sample, do you do the analysis and have the data then?
Well, no, most of the samples that are sent in would never be analyzed because they won't become interesting. So for example, if you're in good health and you send a sample every 6 months for 5 years and you remain in good health, and we have several other men of similar age we could use for controls in an experiment, we might not ever use yours. If, on the other hand, you send in samples for a couple of years and then you develop an interesting disease, then you probably not only be analyzed by us, but by colleagues in other institutions.
Okay. Well, I was curious why you were saving the samples, why you wouldn't just run it and get the data.
It's
just because it's costly to do each individual sample.
The cost of analyzing 200,000 samples is very high, and you don't need those. You need out of this group to get the interesting sets.
Okay, I understand.
You
now.
understand?
Yeah, I understand now. Okay.
And so that's the idea. So if your sample if you never became, hopefully, if you're lucky, and during our time period you never became medically interesting, and you weren't in the beginning, we probably have quite a few men in that category, and your samples might never go out to people.
You have to periodically sample some of them and they'll find out who was interested.
Yeah, well, that's right. But if we hypothesize where this research might go, it's perfectly possible that 10 years from now, all of them would have been looked at, but not initially. And in our case, we'd be looking at specific sets. Breast cancer, for example, I did it before with that, so I know we can see it extremely clearly. So if several ladies had the misfortune to get breast cancer, after they started giving us samples, we'd be all on top of that, because I know that this can do a better job than anything in existence. Yeah.
Maybe pack a battery-powered thermometer in with it so you at least know the temperature profile, and even maybe figure out a reusable package that can use some dry ice or something.
Yeah, you can. It's all expensive. Yeah. Multiply your idea by 200,000, and then we're a small research institute. So we're doing what's practical. Is there any other questions? I'm not kidding. I've wanted this for 40 years. I almost got it once. Pauline and I have been working about 10 years together, I proposed, I'm sorry, I have to admit, in those days we used some of your tax money. I haven't touched your tax money for 30 years. Our science is supported in other ways. But we were on government grants. So I got Kaiser Permanente to agree to do 50,000 people if we could get them $6 million. So I proposed to the U.S. government that they give us $6 million, we do this whole thing at Kaiser Permanente, and store it at -80, so it'd still be here. Well, then my spies and informers in Washington told me they were laughing at us in the elevators at NIH. There's a nut out in California that wants to store urine samples from 50,000 well people. They thought this was totally crazy. So he said, you have to come to Washington and lobby. So I did. It's the first time I went to Washington and did anything. I got a new suit, and I got some shoes, and I went to Washington, and I saw a lot of interesting people. I saw Hubert Humphrey, and he wrote a letter on our behalf. Proxmire wrote a letter on our behalf. I got enough letters into the NIH that they said, okay, you can do 15,000 people. And about that time, I'd also done the wrong experiment. I did an experiment showing that vitamin C increased the growth rate of cancer in mice. And so our laboratory was destroyed, and we couldn't do the experiment. It's a bad story, but in any case, our laboratory fell at about the time they were going to give us the money, and that was the only chance in the past. And then the old work, the analytical work was extremely expensive, and we were only measuring 200 compounds, and it was costly enough that it was obviously not practical at that time. We could demonstrate the technique. Now it's different. This thing is, I wish I could show you all the laboratory. It's really something. The machine has been adapted for this purpose, but it depends on a superconducting magnet. It has 75 gallons of liquid helium in it. Noah and his brothers have built all kinds of backup systems, so 5 different electrical systems have to fail before we lose the freezers. And your samples, there'll be 2 or 3 vials, and they'll be stored in different locations. And it really is something. You have to be a chemist to appreciate being able to take, on a chromatograph, you separate things. There's a chromatogram in there, a little peak for different compounds. In this machine, if the peaks are about the size of my finger and maybe separated by a finger width, the mass spectrum is a quarter of a mile long. It's unbelievable. So anyway, I'll stop taking all your time. If you have more questions, come up and talk to me personally. And if you're interested in participating, this was made for the citizens of Josephine County, but you can cut it out too. And thank you to those who are already sending us samples, because we've been doing experiments on access to energy subscribers.